Okay. On page 13, do we finish part B? Page 13. Okay. All right. Do we start part C? No. So yeah. So let's we'll do the rest of page 13 and 14. So part C says let m be the function defined by m of x equals g of negative 2x times h of x by m prime of 2. A two-step process here, or multiple-step process here. We can't just jump into finding m prime of 2. We first have to find the derivative function, and then we can evaluate the derivative at that point. So if you look at how this is set up here, g of negative 2x times h of x, both terms are being multiplied. So the way we involve derivative rule for terms that are being multiplied, we go through a product rule. Right? So product rule, f prime g plus f g prime. So see if you're able to identify each portion's part and build out your derivative using product rule. Just be reminded, g of negative 2x has a little bit of chain rule inside. So, try that. Okay, so page 13 in your packet. Okay, so f prime g plus f g prime, g of negative 2x turns into g prime of negative 2x times negative 2, right? Outside's derivative times inside's derivative. So g is the outside portion, so g becomes g prime. We keep the negative 2x, and then we multiply by the inside portion's derivative. Negative 2x turns into negative 2. So all that represents your f prime. Your g stays of h, your f stays of g of negative 2x, and then g prime, h becomes h prime. Okay, now we can involve the 2. So plug 2 into all your x's. G of negative 4 times 2 times h of 2 plus g of negative 4 times h prime of 2. Now we can start looking at the top of the page to see if we can make some substitutions. G prime of negative 4, we can pull that value from our table. H of 2, we can pull that from our graph. G of negative 4, we can pull that from our table. H prime of 2, we can pull that from our graph as well. Now, H of 2 is a little bit trickier just because it looks like we don't know exactly where that y value is. But if you look at your H graph has a slope of negative 1/3, right? So every point is going to drop by negative 1/3. And because the slope is negative 1/3, you know that every x value, every tick mark over, we're going to drop by negative 1/3. So negative 1/3, negative 2/3, negative 3/3. So this value is negative 2/3 here. And then h prime of 2 is the slope of that h graph, which is negative 1/3. And then we're just combining those numbers together. And you'll get to use your calculator on your Friday assessment. Okay, any questions with part C? Part D, is there a number C such that G prime of C equals -4? So anytime we want to look for a guaranteed value, we're always thinking IVT and MVT. Usually those are the two um, uh, theorems that we're trying to apply. But we're going to always try to test out IVT first. That's going to be the easier one, right? It's like, oh, can I find this number on the graph? If I can't find that number, then can I find a number below and above? And if I can do that, then I know the graph's going to have to cross through that value. So let's look at our G prime graph, see if we can guarantee that -4. So G prime, -3, -1, 4, 1, -2, -3. If you look at these numbers here, it doesn't look like we can guarantee G prime is -4, at least not by IVT, right? Because these numbers don't dip below -3, so how can we guarantee that there's a -4? Well, it doesn't work for IVT, but maybe mean value theorem can help us with it. And we know mean value theorem is involving the slope of G, right? If the slope of G can be shown to be -4, then we can guarantee that there's going to be a G prime that's also -4. So mean value theorem is not as, it's not going to be the one that we prefer to do because it takes a little bit longer to get to, but it's a little bit more abstract as well. It's not as easy as just looking at these numbers to see, okay, do I see a number below and above -4? That's a little bit easier to get through. But mean value theorem is the one that is more calculus themed. IVT is still within our course, but it doesn't really involve anything involving derivative or slope. So let's see though. Let's see if we can produce a slope that matches -4 between the two endpoints. Right. So so G prime of C is equivalent to, let's find the slope between the two endpoints. So the two order pairs that we want to use are between -5 and -3. So let's find the slope here. So change in y over change in x. So 10 minus 8, sorry, 10 minus 2 divided by -5 minus a -3. Does that slope match -4? So 10 minus 2 is 8. -5 plus 2, -5 plus 3 is -2. We do get -4. So the slope between the two endpoints is -4. There must be a place on G prime that's -4, even though we don't see it, right? Even though we don't see it. But if the slope is guaranteeing that, there must be a G prime that's also -4. So we can say this, since G of X is continuous on -5 to -3 and differentiable, sorry, I wasn't as careful here. But if we want to do mean value theorem, there's two conditions: continuity with brackets, differentiability with parentheses. And since our slope between the two endpoints at the G of X level is -4, there must be a place then where the slope is exactly -4. So on my G of X graph, if the two endpoints are producing a slope of -4, there must be a place where the slope of the curve is going to match that steepness as well. Okay, page 14. Let functions f and g be continuous second derivatives. The table gives values of functions and derivatives. So let k equals f of g of x, write an equation of line tangent to the graph at x equals 3. So tangent line equation, we're going to find order pair, find slope, to get slope from the derivative. To get to the derivative, what do we have to involve here? What do you see? It's a drill for the medical team. Should double check. Okay, so for part A, find your order pair, plug 3 into k of x, and then build the derivative, plug 3 into the derivative, get your slope. Okay, so try that. Let's see if these steps make sense. And then everything you need is in the table above. Right? Careful how you get your value. You got to do this one thing at a time. You're not able to get this all in one step. So find g of 3 first, fill this in with a number, and then you can do f prime of whatever number that you find there. Okay. I have my order pair, I have my slope, and then put it all together, point slope form. Part B, let h equals g over f, find h prime of 1. What rule do we have to go through to build the derivative for part B? Numerator divided by denominator. We got to do what? Quotient rule. Yeah. So f prime g minus f g prime all over g squared. Except the g and f are flipped around, so just be aware of that. When I say f prime, I mean the derivative of the top. When I say g, I mean the denominator. We've done a problem like this before where we got to take care of that 2x first by doing u substitution. So start off with u substitution, get everything in terms of u, figure out what's the coefficient that's going to be part of this process. Sorry, guys. I accidentally gave you guys the PC packet. They say PC in the front. Yeah. You can return them here and then pick up the AC packet. Nice.
Oh, I'm so tired. I don't know what time it's 7:40 now. Oh, I did my name. It's very tough. It's definitely it is. Thank you. Thank you. I
don't know why he doesn't make this.
Okay, finishing up part C here. Our U value is that 2x. And once we get everything in terms of U, we can see, oh, there's a leftover 1/2 that needs to be part of this process. Okay, so now we can make it go through our calculus procedure. We know the antiderivative is going to make f double prime rise up to the f prime level. So the integral and du are going to drop out because the calculus procedure is going to push this f double prime up to f prime. Now that we have our antiderivative, we're ready to think about our bounds, but there's still a little bit of a mismatch, right? These are in terms of x. Our bound is in, we have our expression in terms of u. Our bounds in terms of x. We got to get these to be the same variables. So we do need to bring that x back in. Now we can safely plug in the 1 and 3. Upper bound first. Minus lower bound. 3 times 2 is 6. 1 times 2 is 2. We can go one step further, right? We have our table of values that we can make another set of substitution. F prime of 6 is 5. And F prime of 2 is negative 2. I get 7/2 at the end. Okay, we'll do a little bit of review each day leading up to Friday, but we're kind of circling around the same topics here. So tomorrow we'll do page 15 and 16. Okay, but let's move over to the very first topic that we covered beginning of last semester, and that was with limits. So this is false. These are a lot of fall semester derivative topics such as limits, continuity, differentiation, related rates, curve sketching, EVT mean value theorem rules, derivative graphs, and particle motion. So we kind of, are seeing some of it even as we just did our FRQ review. But also, there's some things that we haven't seen in a while, so it's good to do a full fall semester review. Okay, so a limit tells us the y value that the function approaches from both sides as the function's x value gets closer and closer towards that number. So, so whenever we want to find limits, we always want to pick points on both sides of the graph and draw arrows towards that x value and see, are the arrows pointing to the same y value? If they are, their limit exists. If the arrows are not pointing to the same destination, then the limit does not exist. Okay. So it doesn't matter what's happening at that point. As long as the arrows are consistently moving towards the same y value, that's enough for our limit to exist. So let's try number 1 here. Limit as x approaches -3. We see that -3 doesn't, well, it does exist, but there's a hole there. But we know that limit is not talking about the order pair, it's talking about the approach towards that value. So pick points close to -3 on both sides of -3. And then draw arrows along the path of the graph. Are these two arrows pointing to the same y value? Yes, they're both pointing to a y value of what? Or they're both headed towards a y value of what? 2. Yeah, they're both headed towards 2. You may be tempted to want to isolate that point there, but we know that a point, an island, is never going to be the answer for a limit. It's always going to be the approach or the where the arrows are headed. So both arrows are headed towards a y value of 2. So that is our limit. For number 2, now this is shifting over to just asking for the point. F of -3 is asking, where does a point exist? The point doesn't exist at the hole. The point exists at this dot here. So that y value is 1. So there's a big distinction between limits and order pair if the graph is disconnected. If the graph is connected, then you're not going to tell the difference. Your limit and your order pair will be one and the same. But as soon as there's a break in the graph, whether it's a hole or an asymptote, then we're going to see some, or disconnected graphs, then we're going to see some distinction between limits and order pair. Number 3, limit as x approaches -3 from the left side of -3. So if you see a one-sided limit, it's not asking from the behavior from both sides, it's asking about the behavior from one side. So this is starting to the left of -3 and headed towards -3. So we're only going to follow the arrow on the left. The arrow on the left is headed towards 2. So that's my one-sided limit. As we approach -3 from the right side of -3, we see the arrow is also headed towards 2, but we're only, if you see a plus sign, that means we're only starting with the arrow, with the point on the right, and then we're following that arrow towards that destination. So it's also 2. All right, see if you guys can finish, try 5 through 12, see how much you remember when it comes to limits and order pair. You guys also have the key attached to the back of your packet. Okay, so number 5, as we approach 0, the limit doesn't exist because if I pick a point to the left and to the right of my 0, one arrow is headed towards 0.9, the other arrow is headed towards 2. They're obviously not pointing towards the same destination, so therefore the limit doesn't exist. F of 0 equals 2, that's just a single point. As we approach 0 from the left side of 0, that means we're starting at a point to the left of 0, and then we're following the arrow towards 0, and that's pointing towards a value less than 1. If you say a number that's less than 1, like 0.8 or 0.9 or 0.7, those are probably all going to be fine. We don't know exactly where that value is. This is just our best approximation. Well, that's my approximation. Approaching 0 from the right side of 0, that means I'm following this arrow. This arrow is headed towards y value of 2. Limit as x approaches 2. So if I pick points on both sides of 2, both arrows are headed towards my y value of 1. F of 2 is also 1. One side limit is also 1. The other side is also 1. So when all things match up like this, that indicates that the graph is connected. That means there are no breaks or asymptotes or holes if your one-sided limit and your order pair are all in agreement. Now, at the very beginning of the semester, we would do these algebraic limits, and we would go through factoring or conjugate method or simplifying complex fractions. But now that we have L'Hopital's rule available to us, a lot of that process we don't have to use. I mean, sometimes it may be still easier to go through a conjugate method rather than go through a whole messy chain rule. But typically, I think we're going to prefer to just apply L'Hopital's rule because it's potentially faster to get to the derivative than trying to go through a bunch of algebraic cleanup. But remember that you only can use L'Hopital's rule if you first do direct substitution and you get a 0 over 0. We don't want to just jump into L'Hopital's rule without first confirming that there's a hole. Okay. Sometimes the order pair is already going to be there, or if there's an asymptote, we don't want to do L'Hopital's rule either. So we only want to do L'Hopital's rule after we do direct substitution and confirm that there is 0 over 0. That's the only time you can do L'Hopital's rule. Okay, so let's try example 1, approaching 3 from the left. Whenever you see a one-sided limit algebraically, ignore that one-sided limit. Just think about that 3 there. That one-sided limit may play a role, but it only plays a role if there is an asymptote. Okay? Otherwise, it's just there to kind of distract you. Okay. So first things first, we're just going to plug in 3. What do we get? Numerator, we get 0. Denominator, we get 0. Now, this tells us that's a hole in the graph. The limit does exist. We just haven't found it yet. We could go through factoring, but I think most of us would just prefer to go L'Hopital's rule, especially if the condition for L'Hopital's rule is there. Okay, if you get 0 over 0, you can do L'Hopital's rule. So derivative of the top, just 1. Derivative of the bottom, there's 2x minus 2. Now that we have a derivative version, we can reevaluate. Again, don't worry about the one-sided limit. Just think about the integer value. Okay. I know you may be thinking, oh, wait, when does decimals come into play? It does come into play, but only if there's a vertical asymptote. You get a 10 over 0, 8 over 0. That's the only time that you're going to play with decimals. Okay, so 3 plugs in for x. We get 6 minus 2 is 4. We get 1/4. We have our real number, so we stop. We have our limit. Okay, number 2, limit as x approaches -3 from the left side of -3. First, what's our first step? Plug in just -3, right? Okay, so numerator, we get -5. Denominator, we get 0. Can we do L'Hopital's rule here? No. Okay. We can only do L'Hopital's rule if it's 0 over 0. If you get a -5 over 0 or -10 over 0, a non-zero over 0, this tells us that what's happening here? There's a what? visually what's happening in this graph. There's a vertical asymptote. So there's a vertical asymptote. We know the limit doesn't exist, but if you look more carefully, it's not asking for the full limit. It's asking, as it approaches -3, is it headed towards positivity or is it headed towards negativity, right? If you're approaching a vertical asymptote, there's only two options. You're either going to shoot up to positive infinity or go down to negative infinity. So we're trying to determine this without a calculator, because if you saw a problem like this on the AP exam, this would be without a calculator. So now we can play with decimals. The decimals will tell us which direction the graph is headed. Is it doing this or is it doing this? Okay, so what's a decimal value to the left of -3? That's close enough. Negative what? 3.1, right? So if you're doing within the 10th, that's usually a good enough, close enough for us to determine where the graph is headed. So plug -3.1 in for x. We don't care about the decimal value. We just care whether it's positive or negative. Sorry. This feels like it's hard to do without a calculator, but you just look at this value, right? 2 times -3-ish is like -6-ish. -6 plus 1 is still what? Positive or negative? Negative. And -3.1 plus 3 is negative. So 2 negatives makes positive. So that's enough for me to know, okay, it's going up to positive. My asymptote is causing my graph to shoot up to positivity. Okay, so if we're approaching a real number, we always plug in to see what's going on. We don't know if there's a hole or asymptote, so we always want to just do information gathering as a first step. But if we're approaching positive or negative infinity, we have a different set of process, right? We don't plug in, but instead, what do we do if we see positive or negative infinity? This is end behavior here. So we compare what? Compare degrees. Yeah, so here are the three options here. If your numerator is less than your denominator, that means your denominator is greater degree, then your limit is always going to be 0. If your degrees are the same, then you just take the ratio of the coefficients. If the numerator is greater than your denominator, then limit doesn't exist. It's either positive or negative. So in this case, my numerator and denominator share the same degree. Careful though, the coefficient is a -5 here. So my limit is just 1 over -5 or -1/5. So we have a different set of rules for infinity. For real numbers, you plug in, and then when you plug in, you use that result to help you decide what to do. With infinity, we compare degrees. All right, number 4, first steps first. What do we do? Plug in. What? Plug in 0, right? So we get sine of 0 divided by natural log of 2e to the 0. E to the 0 is 1, 2 minus 1 is 1. So sine of 0 is 0, natural log of 1 is also 0. We have a perfect condition for L'Hopital's rule. So we can find the derivative of the top and the bottom and then reevaluate. So here are some reminders here. Sine of u becomes cosine u times u prime. Natural log of u is just u prime over u. E to the u is just e to the u times u prime. So we can just find the derivative of each of the top and bottom separately and then reevaluate. So sine becomes cosine. Natural log of u becomes u prime over u. U prime for 2e to the x is just 2e to the x. So 2e to the x over 2e to the x minus 1. And once we have our derivative, then we can plug in again and see if that will get us down to a real number where initially we're getting zeros. Sorry. So sine of x becomes cosine of x. This is my u value. So natural log of u becomes u prime over u. 2e to the x minus 1's derivative is just 2e to the x. The U value is just the original value, the original U value. Now that we have our derivative version of our expression, replace every x with 0 and see if that will lead us down to a real number instead of 0 with 0. So cosine of 0 is 1, 2e to the 0 is 2, 2e to the 0 is 2, 2 minus 1 is 1. So 1/2, 1 over 2 over 1, or 1/2. Okay, let's review continuity. Sorry, running out of time here. Let's see. We're going to pick up where we left off tomorrow, but for homework, just one page here. So back to that AP review packet. Page 13 through 15 is your homework. Right. We already did page 13 and 14, so you'll show me that tomorrow in addition to page 15. I'll send out a reminder this afternoon. All right, come get your funds. Mm-hmm. Yep.
7, 8, 9.
Can you show me 1 through 6? You get 1 through 6.
In this packet?
Uh-huh. Yeah. Because I mixed a few off. Okay. Okay, great. Thank you.
79.
Yeah. Okay. And then. Okay, great. Thank you.